Hello, hello. In this video, we are talking about galvanic and voltaic cells. You've heard them mentioned in the past in this unit in terms of a galvanic and voltaic cell taking that chemical potential energy from a redox reaction and converting it into electrical energy. Galvanic cells are able to do this because those redox reactions involve that transfer of electrons. As the electrons transfer from one to another, we can create an electrical current. That electrical current is a flow of electrons, so we can use that flow of electrons again for our electrical current, aka electricity. In order to use that current or that electricity, we have to separate the place where oxidation is occurring from the place where reduction is occurring so we can flow the electrons in between those two separate places. Current is the number of electrons that flow through the system per second. We measure that in units of amperes or amps for short, abbreviated with a capital A. An amp is 1 coulomb of charge per second. A coulomb is a relationship to the number of electrons that we have. We're going to learn more about that later this unit. A voltaic cell or galvanic cell, same thing, is a battery where we're taking a chemical reaction and converting that energy into electrical energy that we can use. Because it is a battery, it is thermodynamically favorable, aka spontaneous. Whenever we have a spontaneous redox reaction happening, the E0 cell that we calculate will always be positive. So throughout the rest of this video, we're going to be talking about the parts of the galvanic cell and how it functions to create that electrical current. So the first parts of the cell that we need to look at are our anode and our cathode. The anode is a place where oxidation occurs, and the cathode is a place where reduction occurs. The anode and the cathode are those actual solid metal pieces that are sitting in the solution in our two separate containers. Remember, we have to separate oxidation and reduction in order to use this current. So in the chamber that contains the anode, again, the anode is the actual piece of metal, is where we have oxidation happening. In the chamber with the cathode is where the reduction process is happening. We also have a saying that we can use to help us remember that the anode is oxidation and the cathode is for reduction. That saying is an ox and a red cat. So that saying, an ox and a red cat, means the anode is oxidation and the cathode is for reduction. So let's apply some actual elements here to oxidize and reduce so we can learn a little bit more about what is happening in this process. Let's say that our anode is zinc. If our anode is zinc, our zinc is going to be losing electrons, oxidation is lost, to form Zn2+, which would then exist in this purple aqueous solution that we have here. So we have solid zinc turning into zinc 2+. Our anode is actually going to be losing mass over time as the reaction occurs. To help us remember that as our solid anode is turned into ions through the loss of electrons, that we are losing mass over time, we have another little saying. The anode is anorexic. So let's go and look at a possible reduction reaction. We can use copper as our possible reduction reaction. Reduction is the gain of electrons. So copper ions in solution are gaining 2 electrons to form copper solid. As those electrons are gained at the cathode and we form that copper solid, our cathode is actually going to be gaining mass as the reaction occurs over time. So we are plating copper metal onto the cathode in the reduction chamber here. So we have yet another saying to help us remember that our cathode is gaining mass over time. And that saying is fat cat. So gaining mass over time, we have our fat cathode. So we're going to move on and look at the next part of our cell. The next important part of our cell that we need to understand how it is functioning is the salt bridge. So the purpose of the salt bridge is to provide a balanced charge between our anode and the cathode. It's going to provide ions in order to balance that charge. It's necessary to balance that charge in order to complete the circuit. So within our salt bridge, our negative anions are going to flow to the anode, and our positive cations will flow to the cathode to balance out that charge. The salt bridge is an essential part for a galvanic cell. Without a salt bridge, our cell will not function. If we remove the salt bridge, our charge can't stay balanced, our circuit can't stay complete, our current's gonna slow down, and then it will eventually, actually pretty rapidly, stop creating any current at all as soon as that charge becomes unbalanced. So let's look at where our salt bridge is and how it keeps that charge balanced. We can see the salt bridge here is this white piece that is in between the two different chambers. Now it's the white piece that I just highlighted yellow. So that salt bridge is actually a salt, aka ionic compound. The most common salt that we use in a salt bridge is going to be potassium nitrate. So as we said, our anions are going to flow to the anode. So the anion from KNO3 is NO3 minus. So those become aqueous ions in solution. We send the negative anions to the anode because we have to balance out that positive charge that is being generated by the zinc 2+. The positive cations are sent into the cathode. The cation in potassium nitrate is potassium. So those potassium ions become aqueous in solution, and we need those positive ions to balance out the negative charge that is building up in our cathode. The next part of the cell we're looking at is the voltmeter. So the voltmeter is going to be actually measuring the cell potential, or E0 cell, in volts. Over time, the voltage in our galvanic cell is going to decrease because we're losing reactants. As we have less reactants, our reaction is going to slow down as we produce more products. We're going to talk more about exactly why that happens when we talk about electrochem equilibrium. So we can see our voltmeter here. That is going to measure the voltage. It measures the voltage as electrons are flowing through this wire that is attached to the voltmeter. The voltmeter is going to be measuring the current, or the electrons that are passing through there, over time to turn that into the voltage. So let's talk a tiny bit more about how these galvanic cells work. One really important thing for how these work is that electron flow. So let's talk more about that. When we look at electron flow in a galvanic cell, electron flow is always flowing through the wire. So it is flowing through the wire that is connected to the voltmeter. It is not going through the salt bridge. The salt bridge is just our K+ and NO3- ions. So through the wire that connects our anode to our cathode, electrons will be flowing. They will always flow from the anode to the cathode, which is alpha order there. We also have another saying to help us remember that direction of electron flow. It is a saying that we have already seen before, fat cat. So electrons will always flow from the anode to the cathode. So let's look at that electron flow on our diagram here. So electrons are flowing from the anode, which we have on the left side, to the cathode, which is on the right side here. In the anode, whenever our zinc is reduced from ZnF, our solid zinc, to zinc 2+, it is losing 2 electrons. Those 2 electrons are sent through the wire as the electrons flow from the anode to the cathode. So those electrons are going to make their way all the way to the cathode. Well, at the cathode, we have reduction happening. Reduction is a gain of electrons. So our copper 2+ ions in solution are gaining those electrons that are flowing to it to turn into that copper solid onto the cathode there. Are all the important parts of a cell that you need to know. You need to know an ox and a red cat. You need to know that the anode is anorexic, the cathode is a fat cat. We need to understand the purpose of the salt bridge and which ions flow which direction, as well as the purpose of our voltmeter and the flow of electrons. One other important note on our voltaic cells. Sometimes in voltaic cell, we're going to have an ion-to-ion or ion-to-gas reduction or oxidation reaction happening there. In the traditional voltaic cell that we just looked at, we had ion-to-solid and solid-to-ion for those reduction and oxidation reactions that we just saw. If we have a gas or converting one ion to another, we have to use an inert electrode. Remember, inert means that it does not react, so it does not take part in the redox reaction. It is simply providing a surface for the electrons to transfer on. Most commonly, we're going to use platinum or graphite. Platinum would be the expensive option, and graphite is a nice cheap option. Graphite is just carbon. So let's look at an example of what ion-to-ion or ion-gas redox would look like. For ion-to-ion, we might have Fe2+ forming the Fe3+ ion. So this would be our anode where we have oxidation happening. As Fe2+ turns into Fe3+, it is also going to be losing 1 electron, which would then flow from the anode to the cathode where we have reduction happening. So on this reduction side, let's look at an example of a ion-gas redox reaction. So in the ion-gas reaction that we see here, our 2 electrons are gained at the cathode where we have reduction happening, and we are generating hydrogen gas. So we're actually going to have bubbles of hydrogen gas coming up from solution as it is formed. Again, both of these processes would require an inert electrode that is not participating in that redox reaction. So we're going to look at a practice problem involving what we've learned about the structure and layout of our galvanic cell. So in this practice problem, we have a setup for a typical electrochemical cell. It contains 2 standard half cells, and it operates according to the question below. So this is an old AP question from 2002, still a great question. So we see our reactions, zinc and nickel are reacting, but down in our diagram, they're just labeled M and X. Part A asked us to identify M and M2+ in the diagram and specify the initial concentration for M2+. While in Part B, we want to know which of the metal electrodes is the cathode and write the balanced chemical equation for that. Pause the video and go ahead and give Part A and Part B a try. Okay, so as you started to look at this, again, one of the first things you realize is that M and X were unlabeled in that cathode. We need to figure out who is zinc and who is nickel. So first off, we can determine who's oxidized and who's reduced in our balanced chemical equation here. Zinc goes from 0 to +2, so it is oxidized, while nickel goes from +2 to 0, therefore nickel is reduced. Well, we're looking for M and M2+. Oxidation happens at the anode. Reduction happens at the cathode. Well, this gives me a flow of electrons. I can use that flow of electrons to determine what my anode is and what my cathode is. electrons always flow from the anode to the cathode. Being the case, that would mean that the left side is my anode and the right side is my cathode where reduction is happening. Well, M is in our anode. Anode is oxidation, so M, the solid anode, must be our solid zinc. The M2 plus in solution would be our aqueous zinc. It does say to identify both, so be sure you specifically identify both. You might have been stumped by that initial concentration of M2 plus. That's just simply a definition. If we read carefully, we saw that we were in 2 standard half cells. A standard cell is always 1 molar solution. So once we figured out A, B should have been really easy. We have reduction happening at our cathode. The cathode is the element being reduced, which is nickel. So nickel must be our metal at the cathode. At the cathode, we have reduction, so we need to show that gain of our nickel 2 plus of 2 electrons to form the solid nickel. Lastly, part C, we want to know what would happen to cell voltage if the salt bridge was removed. Take a moment and think about that. And pause the video. So you might have recalled or looked back in your notes to see that cell voltage will drop to 0 over time if we remove that salt bridge. You just had to squeeze this last part in a bit, but if the salt bridge were removed, cell voltage will drop to 0 because there would be no ions to balance out the charges. Remember that the ions are going to balance out the positive charge buildup in the anode, and we also need them to balance out the negative charge buildup and balance out the negative charge buildup in the cathode. You have another free response practice question on page 28. Please try out free response question number 2 on page 28 on your own. We will be going over this in class next time we see you. So again, please try that out on your own. So hopefully we're getting some good practice in with our cell layouts.